Okay, so I've started recording again, all right? So, so I want to introduce two things here. So first of all, let's think about the fact that eventually uh, we're going to want to be graphing functions, okay? So stuff that you would have seen in advanced functions, the course before this, is you would have learned about end behavior. So is a function approaching positive infinity? Is it approaching a horizontal asymptote? Okay. Now we're seeing about, you know, increasing and decreasing. So let's say I've got an asymptote here and it approaches zero as x goes to negative infinity. Okay. And now other ways that we can describe this, we say, oh, the function is increasing on this interval. Then maybe the function is decreasing. It's got an x-intercept. Oh, it has a local minimum as another x-intercept. Maybe it has another local maximum here. Okay. And maybe it goes back up and maybe does something like this. Okay. So when you take a look at the characteristics of this graph, okay, so obviously the end behavior approaches zero as x approaches negative infinity. Here approaches positive infinity as x approaches positive infinity. Okay. You're able to find, say, vertical asymptotes. You find the x-intercepts. Now we have a way of finding the local maxima and minima. Okay. And you could determine when something's increasing or decreasing. But you kind of notice here, there's no maximum or minimum, that this function has a bit of a squiggle. Okay. But it doesn't really fall into any of these other categories in terms of figuring out where and why it has this squiggle here, because, you know, it's increasing, but it keeps increasing all the way through. Okay. It's not like here at a local max or min where it changes from decreasing to increasing or increasing to decreasing. Okay. Or here at an x-intercept, it goes from positive to negative, negative to positive. Okay. So what we want to do is we want to take a look at how we can determine this kind of behavior. Okay. But before we get to that, here's a question for you. So let's say I'm going to let's say I came to this class and I said, hey, folks, I've got a great stock for you to buy. In fact, you can buy two stocks, and they're both fantastic stocks. It doesn't matter which one you buy. I think one is just as good as the other. Okay. So let's say at the beginning of the year, the stock started at $2, and now on April 25th, the stock is at $10. So really good. It went up by 5 times. And then there's a second stock that at the beginning of the year was also at $2, and now it's also at $10. And even better than that, the stock price has been increasing for the whole time. It never took any dips. It was continually increasing. Okay? So listen to that scenario. And January 1st starts at $2. Now April 25th, $10. Same thing for both stocks. And both stocks have been increasing the whole time. So do you think it matters which stock you buy? Because they're both always getting higher, and they started at 2, ended at 10. What do you think? Who thinks you should buy you could buy either stock? Okay, so I see somebody who's saying no, they're not both the same. Anybody else who thinks that they would be one as good as the other? Okay, I guess everybody here. Okay, you sell the same on the 25th. Yeah. Oh, I'm buying it today. I'm using the past behavior to see. There you go. Exactly. Okay. So, who wants to tell me? And maybe Maxwell, you can tell me, or somebody can say why Maxwell says no. The two stocks aren't necessarily one as good as the other. Okay. What information do I not know based on what I told you? So I said starts at 2, ends at 20, and always increasing. Why might one stock be better than the other if I had to decide on uh, on selling it today? Yes. What about just the numerical stuff? We're not, this is, let's face it, this is not a this is not an economics course. So we're not going to get into the weeds. We're just going to look at the mathematics here. Remember, all I told you is that it's always increasing. What did I not tell you though?
How much it increased by?
Yeah, I didn't tell you how it was increasing. Can you see that maybe one stock is increasing slowly at first and then starts increasing faster and faster and faster? Okay. Then the other stock maybe increases quickly at the beginning, but then starts to level off. Okay. Did they both start at 2 and end at 10? Yes. Were they both increasing the whole time? Yes. But if you had to choose, would you choose stock one or would you choose stock two if you had to buy it now? Based on these graphs, which one would you choose? I think pretty much everybody would choose stock one because you're saying, oh, look at that, it's on the increase, or this one, it's slowing down the increase. Okay. So this is where we notice that the information that the first derivative gives us, which is just that it's increasing or decreasing, doesn't necessarily tell you the whole story. Okay. So, and this is where I want to make a connection to this graph. Because if you kind of look here, it kind of looks like in this portion, up to somewhere there, it kind of has the look of function 2. And then afterwards, it has the look of function 1. Okay? And let's try to describe that. All right? Now, you might have heard me say word before I asked you, have you talked about concavity? Okay. Now, when you look at the way these two functions are shaped, can you sort of see it kind of looks like whether something is concave or convex? All right. If you think of like lenses, if you wear eyeglasses or you have concave or concave lenses, but they decided to just stick with concavity to describe this type of behavior versus that type of behavior. But if we're not going to use concave and convex, we're just going to use concave. Does anybody, can anybody think of a function that you would have studied quite a long, quite a lot that had sort of this behavior that looks like this one here as opposed to that one there? Okay. And think of how it's curved. Okay. This one is curved sort of upwards, whereas that one is curved, whoops, is curved downwards. So what I want you to imagine, and I'm going to try to find a tool here. Give me just a second. So think about, yeah, log x for sure. Oh, I want you to think something even simpler than that. Even simpler. Oh, here, I think I got something that works. Exponential function, that's another good one, even simpler than that. And so you got to go back to like, early high school. All right? Is I want you to think of parabolas. Okay? And these were the two types of parabolas that you had. You had this type of parabola and you had that type of parabola. And how did you describe the difference between these two types of parabolas? Okay? You probably would have said that this parabola opens upwards and that parabola opens downwards. Yeah, and of course you can get transformations out of all of that. Okay? So what we say is that this first function here is concave up because the function sort of opens upwards, and this one here is concave down. Okay. And one way to think about it is imagine I start with imagine this is a completely straight piece of wire. And if I bend it upwards, I create something that's concave up. And if I bend it downwards, I create something that's concave down. Okay. And this is going to help us describe these sort of squiggles in the function when you have something that's concave up Like an exponential function, e to the x opens upwards, whereas a logarithmic function opens downwards, okay? A parabola with a positive leading coefficient opens up, and the parabola with the has upward concavity, and a parabola with a negative leading coefficient has negative concavity, okay? So let's take a look at this function here. So in this first section, what do you think? In this first section, is concave up or concave down? Is it bending upwards or bending downwards? So again, imagine this was straight. Yeah, bends upwards. There you go. So concave up. Now, can you sort of see in this section here, it's concave up still. It's still bending upwards. Okay, it's concave up. Now I want you to stop me when you think it stops being concave up. So I'm going to move my pencil. Tell me when you think it stops being concave up. Up, 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 up. Tell me when to stop. Tell me when to stop. Is it still concave up? Yeah.
It's
Can you
kind
see at
of
this point here, it starts being concave down? Okay. Wait, I just want to see if somebody's trying to come in. Yeah. Okay. So somewhere around here, it's hard to know exactly when it happens, but somewhere around here, it changes from being concave up to being concave down. And then, wait a minute, somewhere here, can you see? It's hard to tell exactly where it happens, but you see that somewhere here, it changes from being concave down to being concave up. And then here, at some point, it changes from concave up to concave down. And then at this point here, it changes from concave down back to concave up. So this here, it's still concave up. Then maybe in this section here, it's concave down. Then in this section, it's concave up. Okay, then in this section, it's concave down again. And then finally in that last section, it's concave up. Okay, so this now is going to be a new characteristic that we find. Yeah, so we're going to get there in a second. I see the question in the chat. We're going to get there in a second. Okay, but this is going to again help us to draw this graph, is to know this behavior that when the function, oops, I lost my piece of wire. I can't find it. Here, I'll use a ruler. Okay. Okay. Try not to break it here. That we're going to know when this function is concave up or concave down. And that's going to help us draw the graph. Okay. So these points where that change happens, well, they're going to be important points to know because I want to know exactly. Here, it's hard to tell exactly where it stops being concave down and starts being concave up. Even here, that happens somewhere on there. Eventually, we want to find those exact points. And those are what we call points of inflection, okay? Where a function changes concavity from up to down, or from down to up. And those are our points of inflection. Okay. Now, how are we going to find these? Okay. So I'm going to draw a different diagram. Okay. Just to kind of give me more room. Okay. So somewhere around here, again, hard to tell exactly where it happens. This function is going to change from concave down to concave up. Okay. Now, given that this is a calculus class, we have to imagine that we're going to look at the derivatives. Okay. Now, the problem with this example is that the derivative, maybe you know what? I don't like this graph. I'm going to draw another one. Forget that. Sorry. I want to draw one that's less complicated. I should have drawn a little nicer here. Let's just do this. And somewhere here, hard to tell exactly where, we have our point of inflection, okay? Where it changes from concave up. So as I just said, you know, presumably we're going to use derivatives, right? This is a calculus class, so we're going to use derivatives. But what do you notice though? Before and after, the function is increasing, okay? But even after that point, the function keeps increasing. So the problem is that the derivative itself, or at least the sign of the derivative, doesn't tell us anything directly about concavity. It's just telling me that it's increasing before that point, increasing after that point. So there's nothing particularly interesting. So it's not about the sign of the derivative, but this is where now I want you to tell me what happens to these derivatives as I move from left to right. So what can you tell me about that slope of tangent? What kind of slope is this going to be if I start on the left here? What kind of slope is that going to be? Well, what's the easiest thing you can tell me about the slope of that tangent? Oh, actually, no, I think it's positive. As you see, yeah, it's positive because it's increasing, okay? And can you see that it's pretty steep, okay? So not only is it positive, but it's also pretty steep, okay? So now, as we move from left to right, what about this? Is that more positive or less positive? Is that a bigger slope or a smaller slope? This second one here. It's smaller, yeah, because you're going for something steep to less steep. And then let's look at this. Even smaller, even smaller. Are you noticing what's happening? The slope's still positive. Yes, exactly. Very important. Still positive, but getting smaller and smaller and smaller. Okay. And you see they're going to get flatter and smaller and smaller. And then we're going to get to this point here. But now, and let's see if I can get a different color. Unfortunately, the colors are not showing very well here. We'll try green, if you can tell the difference here. What starts to happen? So here, the derivative is never actually zero. Notice here, even at this point of inflection, the derivative, it's not a horizontal derivative, okay? But they do get smaller and smaller and smaller. But then after this point, what starts to happen with all these tangents? What happens to the slopes of the tangents after that point? They started by getting smaller, 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 smaller. And then after that point, what started happening to those slopes of tangents? Can you see that they start getting bigger and bigger and bigger and bigger and bigger? So here we see that in this interval, f prime is increasing. And then in that interval, after that point, the derivatives are decreasing. Okay, is everybody okay with that?
I have a
Okay.
question. Would it
Yeah.
not also be increasing? I mean, increasing on both sides?
Well, remember, I'm always when you're looking at a function, you're describing a function, you're going from left to right. And here, remember, I'm just talking about the slopes of the tangent. I'm just talking about the derivative, not the function itself. So notice here, I'm not saying that the function is increasing here and the function is decreasing here. It's the slopes. Remember what the derivative represents. It's the slopes of the tangents are increased, sorry. Oh, man. I wrote it wrong. I said it right and I wrote it wrong. Sorry about that. Sorry,
Okay.
maybe was that what you were telling me?
But even though,
Yeah.
would it still not make sense if because the slopes looks like they're still increasing on both sides.
Yeah, no. I made a mistake. I wrote it wrong. I think I explained it right, but I wrote it wrong. Let's do it again. Let's take a look here. Sorry about that. I apologize. I guess I was getting too excited here. I wrote something wrong. Let's take a look here. Yeah. So here You see how they're starting very positive and they're getting less and less positive. They're getting smaller and smaller and smaller. So that means the derivatives are decreasing here. And then at this point, you see how the derivatives now start increasing. Okay, so remember, I'm not talking about the function, I'm talking about the slopes of the tangents. Here, as I move from left to right, the slopes of the tangents get smaller and smaller and smaller and smaller and smaller. And now, once you get to this point, the slopes of the tangents start getting bigger and bigger and bigger and bigger. Okay? So here now, in this interval, the slopes of the tangents are increasing. Okay, sorry about the mistake there. Okay, so let's do it one more time. They go from decreasing because they're getting less and less positive. Okay, then at this point, there's the derivative, but now on the other side, the slopes start increasing again. Okay, so now we see we're not talking about the sign of the derivative, we're talking about the derivative increasing or decreasing. Wait a minute. What tells us that something is increasing or decreasing? What did we use before to show that something was increasing or decreasing? Remember how we determined that something was increasing or decreasing? The derivative of that function had to be positive or negative. So if the first derivative is decreasing, wait a minute, let's look at its derivative, the second derivative. What has to be happening with the second derivative if the first derivative is decreasing? Remember what the rule was, that if a function was decreasing, its derivative should be what?
Negative.
Exactly. But here, I'm not talking about the function decreasing, I'm talking about the derivative decreasing. So if the first derivative is decreasing, then the second derivative has to be negative. And here, if the first derivative is increasing, so it's getting bigger and bigger and bigger, what has to happen? The second derivative must be positive. And this is how we can determine concavity, not by the sign of the first derivative, but the sign of the second derivative. Okay? So let's take a look at some of these other examples here, because here it looked like we had a point of inflection. So let's see what's happening here. So can you see the slopes are very, very negative here? If I start at this point here, the slope of the tangent is negative, okay? And now what's happening? As I move to the right, it's getting less and less negative. Wait a minute, is the slope increasing or decreasing as I'm moving to the right? So what happens if I'm going from -10 to -8 to -6 to -4? Are those numbers increasing or decreasing? Increasing, exactly, because they're, imagine on a number line, as you're going from, if this is 0, as you're going from more becomes less negative, you're increasing. So let's see what's happening. So less and less negative. So they're increasing, they're increasing, they're increasing, increasing. Eventually it gets to 0. Does it keep increasing after this point? Yes, because they're getting more and more positive. So they're getting, there you go. They're getting more and more positive, increasing, increasing, increasing. But once I get to this point, can you see that when I go past that point, the slopes of the tangents start decreasing again? You see how they're decreasing and decreasing and decreasing, and eventually they get to 0. And then they get even more negative, getting smaller, getting smaller, getting smaller, getting smaller. But then once I get to this point, what's going to start happening now with the derivatives if I keep going? Getting bigger and bigger, getting more positive, more negative, sorry, less negative. There you go. You get to 0. And we start to see that wherever the derivatives are increasing, it's concave up. And wherever the derivatives are decreasing, it's concave down. Okay? But since we're talking about the derivative decreasing or increasing, we have to look at the sign of the second derivative. Okay? So I think what would be useful to do now is to actually look at a function on Desmos and see if what I'm talking about is making any sense. Okay? So I'm gonna stop this here and let me just open up a tab for Desmos. Give me just a second. Okay. And let's see if this makes sense, because it's all very nice me showing you that my pencil moving around, but let's let Desmos kind of be the final arbiter here. Okay. So give me just a second. I'm going to come up with a function here. Here we go. All right, so let's take a look here. So I define this function. In fact, I don't need to go quite so far out. Let's go to like 3. There you go. So we have this function. You can look at the equation there, similar to the one we had before, except instead of e to the 2x, it's just e to the x. Okay, and let's see if we can figure out where it's concave up or down. So in this section here, is it concave up or down? Is it curving upwards or downwards here?
Upwards.
Yeah. And do we want to guess where it changes from curving up to now being concave down? I don't know. Guess a point. Let's take a look. What is it? Maybe at, I don't know.
At x equals -3.
Yeah, x equals -3, maybe -4, but somewhere around here, can you see that it's changing from concave up and then it's becoming concave down? Okay, here, so it's concave down, concave down. Oh, whoa, 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 it becomes concave up again. You see that? Where does that seem to happen? I don't know, maybe -0.5, somewhere here? That seem reasonable? That it changes from concave down to concave up? Okay. And then does it ever become concave down again? No. Okay. Now remember what we said. We said that we expected the first derivative to be increasing if it's concave up and to be decreasing if it's concave down. Increasing if it's concave up, and apparently. So let's test this first derivative and let's see if our first conjecture was correct. Oh, hey, look at this derivative, the blue function. Do you see how it's increasing to about, oh, look at that, to negative 3.7. That's about what we had estimated. And now all of a sudden, in this area here, it's decreasing to about, oh, I said about negative 0.5, but about negative 0.3. So do you see in the area where the original function is concave up, the first derivative is increasing. In the area where the function is concave down, the derivative is decreasing. And then in the area where the function is concave up again, look at the derivative. It's increasing. Okay, so can we see that this fits what we saw before? Okay, now let's look at the second derivative because we said, well, wait a minute. If the first derivative is increasing, the second derivative should be positive. If the first derivative is decreasing, the derivative should be second derivative should be negative, and if the first derivative is increasing, the second derivative should be positive. So let's shut this one down and let's now look at the second derivative. And let's see if we were right. And look at that. Concave up, positive second derivative. Concave down, negative second derivative. Concave up, positive second derivative. All right. And where are the points of inflection going to happen? Remember, where it changes from concave up to concave down. When it changes from concave down to concave up. So where are we going to find those points on the second derivative? When does the second derivative change sign? At what special points? At the x-intercepts of the second derivatives. Exactly. Okay. So now, what I want to remind you folks is that this is all very nice because what is something we know how to do well? We know how to determine when a function is equal to 0, and we know how to determine the sign of a function when it's positive or negative. So now we see you can find the zeros of the functions to find the x-intercepts. Okay, and let's actually put the derivative back in. Okay, now we have all three functions. So when you want to determine the x-intercepts, you can determine the x-intercepts of the function and then use that to find when the function is positive or negative. Then with the first derivative test, you find when the first derivative is equal to 0. Okay, and you can use that to help you determine when the first derivative is positive or negative. In other words, when the function is increasing or decreasing. Okay, and help you find those maxima and minima. Now you do the same thing with the second derivative. You determine where the second derivative is equal to 0. Okay, and then wherever it's positive, the original function is concave up. Wherever it's negative, the original function is concave down. And where the second derivative is 0 is where you might have points of inflection. So you see it's the same algebra that you're using, finding x-intercepts, finding the sign of a function, yet you're determining different pieces of information, whether you're working with the function, the first derivative, and the second derivative. And there's nothing better in mathematics when you can recycle the same processes to determine new things. Okay, so let's kind of write this up now. Let's kind of write this up and see if we can now come up with a strategy for doing these problems. So here, let me go back to sharing my thing here. Okay. So let's write out what we found. Okay. So let's start with concavity. Okay. We saw that if f prime at x is, sorry, f double prime at x is positive on an interval, okay, what does that tell us about the function when the second derivative was positive? Who remembers what that tells us about the function? So remember, we're using information about the second derivative to tell us something about the function. When the second derivative was positive, what was the shape of the graph? Remember, on that section, it's concave up. Then f is concave up on that interval. Okay. If the second derivative is negative on some interval AB, then we saw that the function f is concave down there. Okay, so concave up, concave down. Okay. So now this is information that you can get about the function. Okay. Now we're going to look at points of inflection. What has to happen in order for there to be a point of inflection? What's the special thing? Can somebody tell me what's the special thing that has to happen at a point of inflection? Look at the picture that I've just drawn you. What happens before and after that point? What is it that changes? Yeah, but just describe it. Yeah, the concavity changes. Look at this example here. It changes from concave down to concave up. Okay, or I could draw it like this. That's also a change in concavity. This is also a point of inflection, because here it changes from concave up to concave down. And that's what you need to have in order to have a point of inflection. Okay. And since the concavity has to change, it means what has to happen with the sign of the second derivative? It needs to change. So here, the second derivative must be changing from negative, where it's concave down, to positive, where it's concave up. Here, there's a point of inflection, but it's the other way around. The second derivative goes from positive, concave up, to negative, concave down. And that's what gives you your points of inflection. Okay. So points of inflection are points where the concavity changes. Okay, and it could be from up to down or down to up. Okay, and how do we find the points of inflection? Okay, so to find them, let's give a procedure for finding them. Okay, is solve for when f double prime at x is equal to 0. Okay, so if f double prime is equal to 0, and that's not the only thing that has to happen, okay, the concavity has to change, but in order for the concavity to change, the sign of the second derivative has to change. Okay, so if the second derivative is 0 and the second derivative changes from negative to positive, or positive to negative, then there is a point of inflection. Which often we call POI. So not sometimes we use POI for point of intersection. Here we're using it for point of inflection, but it should always be clear which one we're talking about. Okay. Now, if f double prime at x is equal to 0, but the sign does not change, then there's no point of inflection. Okay, so there has to be a change in sign in order to have a point of inflection. Okay, not enough just for the second derivative to be 0. But this should look familiar, because remember, if the first derivative is equal to 0, are you guaranteed a local max or min? No. Okay, you might have one. That's where you're going to look for local maxes and mins, but there's no guarantee that there's going to be one. Same thing here. Okay, if the second derivative is equal to 0, there's no guarantee that there's a point of inflection. And let's look at two easy examples. Okay, and I'm going to take functions where I know if there's a point of inflection. Let's take y equals x cubed. Okay, now I should already know where y equals x cubed has a point of inflection. Hey, it's got one at 0, 0. Okay, because it goes from concave down to concave up. But let's actually solve the problem. Okay, so let's find the first derivative, 3x squared. Let's find the second derivative, 6x. Okay, so let's make the second derivative equal to 0. All right, so 6x equals 0. When does that happen? Hey, at x equals 0, just like we anticipated. Okay, and now I'm going to do what I did before. I'm going to test the sign, but now the sign of the second derivative. So 0. So let's put in -1. What's 6 times -1? It's a negative number. Let's put in +1. 6 times 1 is a positive number. And so at 0, is the second derivative equal to 0? Yes. Does the second derivative change sign at 0? Yes. Okay. So based on what we're seeing here, it's concave up on -infinity to 0. Okay, sorry, concave down, because the second derivative is negative, but it's concave up on 0 to infinity, because to the right of 0, the second derivative is positive. And that's exactly what we expect. And we have a point of inflection at x equals 0. Okay. So I followed the strategy and showed that there's a point of inflection. But now let's take a look at x to the 4th. Now again, I already know what x to the 4th looks like. Kind of looks like a flattened parabola, right? So let's find the derivative, 4x cubed. Then let's find the second derivative, 12x squared. And where is the second derivative equal to 0? Hey, again, at x equals 0. Now, if I was just doing this without knowing the graph, I would say, maybe there's a point of inflection at x equals 0. Knowing what the graph looks like, I look at it and I say, oh, wait a minute, there's no point of inflection there. So let's make sure our note here works. So let's now take the sign of the second derivative. Okay, so let's take -1, and that's when I realize, hey, -1 squared is positive, times 12 is positive. But then to the right of 0, if I pick x equals 1, 12 times 1 squared is still positive. So did the second derivative change sign? No. Okay. So is there a point of inflection at 0? No. Just because the second derivative is equal to 0 doesn't mean there has to be a point of inflection. And here's an example where there's no point of inflection for y equals x to the 4. Okay, but since it's positive everywhere, it's concave up everywhere. Okay, and when you look at the graph, does that make sense? Yeah, it certainly doesn't. It certainly does. It's concave up. Okay, so now that you have finding x-intercepts, finding end behavior, finding vertical asymptotes, finding increasing or decreasing, finding maxima and minima, finding concavity, and finding points of inflection, finally, you're going to have enough information to put all that stuff together and sketch the graph of a function. Okay? So it's about putting all these things together. But for now, let me give you an example of finding points of inflection and concavity. Okay, so I'll give you this function here, x squared e to the x. Okay, so what I want you to do is determine if this has any points of inflection, all right, and tell me when it's concave up and when it's concave down, all right? And be very careful when you're taking the second derivative. Make sure you take the first derivative correctly and then second derivative, okay? Because it's going to take a bit of time to take these derivatives. All right, go ahead. Okay, folks, I can give you another 3-4 minutes. Okay, so again, make sure you're checking, you're being very clear with your derivative. And your second derivative, of course. Okay, so I think we should take this up here. All right. So since I'm looking specifically for points of inflection and concavity, I'm going to find the second derivative. But again, keeping in mind that eventually we want to get to curve sketching, you're going to be using that first derivative also, okay, to determine increasing or decreasing and to determine the local extreme. Okay, but for now, we'll focus on the second derivative. So let's take the derivative here. Derivative of x squared is 2x times second function e to the x plus the first function x squared times the derivative of the second function e to the x. Okay, So let's check if we have the same answer. Yeah, looks good. Now I have to take the second derivative, and we're going to see this is going to be quite a bit more complicated because I need to use the product rule here, and then I need to use the product rule there. So it's just long, but we'll take it slowly here. So the derivative of the first function is 2 times the second function, e to the x, plus 2x times the derivative of e to the x is just e to the x. Okay. Now let's take the derivative of, hey, look at that. This is the same as the original function. So I might as well just copy what I already have. I've already taken the derivative of x squared to the x. So here it's going to be 2x e to the x, okay, plus x squared e to the x. Okay, there you go. So we're going to see if we have the same answer. It looks like we will. So here, let's do some cleaning up. Well, let's definitely factor an e to the x, and let's see what we have left. Well, we have an x squared. I'll put that first. I have 2x plus 2x plus 4x. Okay. Okay. And then here, it looks like I have a 2. There you go, plus 2. And now we want to determine when this is equal to 0. Okay. So step 1 is to take the second derivative. Now we're going to set this second derivative, I guess for this is bad communication. I should put the 0 here. So here, e to the x, is that ever equal to 0? No. So that means I just have to solve when x squared plus 4x plus 2 is equal to 0. And unfortunately, so here it looks like somebody's already calculated it for us. Let me just write out the exact answer first, and then I'll take your approximated answers. Yeah, good old quadratic formula. Yeah, it makes you really appreciate how much we use the quadratic formula. Okay, so what do we have? Negative b, so negative 4 plus or minus b squared, so 16 minus 4 times 1 times 2, okay, all over 2 times 1, okay? So what does that give us? Negative 4 plus or minus 16 minus 8, so this is just root 8 over 2, and this is approximately equal to, so I'm going to be a bit lazy and I'm just going to keep one decimal place, so I'm going to say negative 0.6 or 3.4, okay? Now, what am I going to do with these numbers? Who's going to tell me what I'm going to do with these numbers now? Because all I determined is where the second derivative is equal to 0. What do I now have to use these to determine? So remember, if I want to determine concavity and I want to determine, no, not yet. That's only if I want the points. What is it I need to determine if I want to talk about concavity and points of inflection? Okay, remember, we have to look at the sign of the second derivative. We have to see if the sign changes or not. So now I'm going to take my second derivative and I'm going to create my number line with negative 0.6 and 3.4. And I'm hoping we're going to remember the trick that I showed you before. Because e to the x is not only that it's not equal to 0, e to the x is always positive. So the only thing that's going to determine the sign of the second derivative is going to be the sign of this quadratic. And like before, what do we have? We have a quadratic with a positive leading coefficient. So our signs are going to look like this. It's going to go from positive to negative to positive. Okay. Again, if you want, you can take values in each of those intervals and stick it into your second derivative to find the sign. You could certainly do that, but boy, this saves me a lot of time. Okay, so now I see at negative 0.6, the sign of the second derivative changes. So there's a point of inflection. So at x equals, and I'm assuming that's negative 4 minus root 8 over 2. but there's also a change in sign at 3.4 or negative 4 plus root 8 over 2. So there's going to be 2 points of inflection. All right. Now let's see where it's concave up. Well, it's concave up wherever the second derivative is positive. So from negative infinity to negative 4 minus root 8 over 2. And it's also positive from negative 4 plus root 8 over 2 to positive infinity. There you go. And where is it concave down? Whereas remember the original function concave down whenever the second derivative is negative. So from negative 4 minus root 8 over 2 to negative 4 plus root 8 over 2. Okay? And so now we're seeing how the first derivative gives us a whole bunch of information, and the second derivative gives us a whole bunch of information. In this case here, it gives us when it's concave up and when it's concave down, and it tells us where we have points of inflection. Okay? So we've got 10 minutes left. We can do one of two things. I can give you another example. I prepared another example, or are there questions people want to ask? Okay. So I have one vote for another example. Does anybody have any questions before I give you another example? Yeah, looks like someone else is liking another example. Okay. And this one here, I promise you there's no quadratic formula. Okay. I'll spare you the quadratic formula for one example. Okay. So here the function is going to be x to the 4 plus 6x cubed minus 24x squared. Okay. So what I want you to do is I want you to find the points of inflection and where the second derivative is positive or negative. Okay. So I said no quadratic formula. That of course is if you take the derivatives correctly. If you make even one little mistake on the derivative, you're going to be stuck probably having to use a quadratic formula. Okay. So let me give you, we'll need about 4 minutes to take this up. So I'll give you about 4 minutes to complete it because these derivatives are pretty easy compared to the last one we did. That one was much harder. All right. So let me leave you with that for about 4 minutes. All right, folks, so let's take this up here. So again, since I'm looking for points of inflection, I'm looking for when it's concave up or down, I know I have to find the second derivative. So let's start by finding the first derivative. So 4x cubed plus 6 times 3 is 18x squared minus 24 times 2, 48x. Okay. Beautiful polynomials that are very easy to take derivatives. And now let's take the second derivative. So here, second derivative. So this is going to be 12x squared. This is going to be 2 times 18 is, I guess, 36x. And then here minus 48. Okay. Now, because I'm looking for the sign of the second derivative and where it's equal to 0, we'll set that second derivative equal to 0. And here, well, there we go. We can factor out the 12. What do we have? X squared plus 3x minus 4. And here looks like this is going to be a nice one, because here we've got, looks like x plus 4 and x minus 1. Okay, so that means our zeros are x equals -4 or x equals 1. Okay, and I see somebody's confirmed that for me, so that's great. Now, of course, remember, this just means the second derivative is 0 at these points. It doesn't mean yet that they're points of inflection. Okay. Yeah, I mean, obviously, that's the great thing about the quadratic formula is you could always use the quadratic formula, but when everything works out nicely, especially here, since you were able to factor out the 12, I'd say, try to factor if it's easy numbers, just because then less chance, quadratic formula, again, decomposition. Oh, no, I hate decomposition. So I'm not a big fan of decomposition, but if it works for you, keep doing it. But I would say when the numbers are really easy like this, it's not worth doing decomposition, because decomposition is great if you have big numbers. I mean, here we had big numbers, but because we were able to factor the 12. But for stuff like this, try to do the factoring faster. That would be my suggestion to you. Okay. And usually when you're working in calculus, we give you pretty easy factoring. Okay. If the numbers are big, I'd probably just put in the quadratic formula. Yeah, good old, see if you can avoid decomposition when you can. Okay. So let's test the sign. Okay, so I want to test the sign of the second derivative. There you go. -4 and 1. Oh, does anybody see what trick I'm going to use here? Who's going to tell me why I'm not going to actually plug in any numbers into my second derivative? What am I going to do? There you go. You notice that it's a parabola with a positive leading coefficient. So it's going to look something like this. So I don't actually need to test the signs. It's going to go from positive to negative to positive. And so that means this function has 2 points of inflection. Okay. So we have a point of inflection at x equals -4, and we have a point of inflection at x equals 1. Okay. Perfect. And did you get these points of inflection, the person who graphed it? Excellent. Okay. And if you graph it on Desmos, you're going to see at these points, it's going to go from concave up to concave down, and then it's going to go back to concave up. Okay. So it's probably going to look like this, as we know this is a quartic, but it's going to go from concave up, then it's going to go to concave down, and then it's going to go to concave up again. So it should look something like that. All right. So 8:59, I think we can end it there. If anybody has some questions they want to ask, I'm happy to answer them. Otherwise, we'll call that a class, and I will post these videos in case anybody needs access to them, or if you know anybody in the class who needs to have a look, you can tell them. Okay, my